Good morning everyone, welcome to today's worked exam answer video, where today I'm having a look at a kind of practical question covering thin layer chromatography, which has come from an AQA A-level paper. So we've got a bit of information to start with about thin layer chromatography. So it says a protein was hydrolyzed to form a mixture of amino acids. A spot of this mixture was added to a TLC plate and the plate was placed vertically in a small volume of solvent 1. When the solvent front reached nearly the top of the plate was removed and allowed to dry. Then it was turned anti-clockwise through 90 degrees and placed vertically in a small volume of solvent 2. When the solvent front reached nearly the top of the plate was again removed and allowed to dry. And this shows what the final TLC plate looked like. So we've got the position of the original spot, which was there, and we can see that solvent 1, which will have been added below that original pencil line, has travelled in this direction. And then once that solvent got to that point, solvent front 1, they've then rotated this way, put the solvent below where the white circles are, and then solvent 2 has moved up there like that. And we can then see that the white spots, some of them have separated more, some of them have just redeposited, and then we've also got, from the position of the original, these ones here. Okay. Now we do need to know how to hydrolyze the protein in the first place. It says suggest a reagent for the hydrolysis of a protein, and we're going to need some sort of very strong acid. So 6 molar, which is really strong. So 6 mole per decimeter cubed hydrochloric acid. And it hasn't asked for the 6 molar here, it says suggest a suitable reagent, but I would argue it does need to be pretty concentrated, and so dilute acid probably isn't going to cut it. It needs to be concentrated, or if you give a specific concentration, I would argue that's also okay here. So I'll put in brackets concentrated HCl. And that will break all of the peptide bonds between the different amino acids in the protein chain. And then we would do thin layer chromatography like this to analyze which amino acids are present. Now, the next question suggests how the positions of the amino acids on the TLC plate were located. Amino acids, unfortunately, are colourless. So unlike chromatography of like the dyes or the inks in black pen, where you would get all the different colours separating out on your chromatogram, because the amino acids are colourless, you can't see anything. So we need to do one of two things. We can either shine a UV lamp onto the TLC plate, and where the amino acids are would show up as like darker patches, which you could then get a pencil and draw around, so that when you then turn the UV lamp off, you can then measure the RF values from there. The other method is to spray the TLC plate with a developing agent, and the one that they want you to know the name of is ninhydrin. So you would spray the plate with ninhydrin and the amino acids would soak that up, and then they turn into like a dark brown, burgundy, sort of purpley colour. And again, we can then measure the RF values because we can see them. Now, for this question, I would argue you could give either answer, because it just says suggest how the positions of the amino acids on the TLC plate were located. Certain questions will ask you to name a developing agent that can be used and to explain why that's necessary. So make sure you're answering the question. So I'm going to put for my answer, spray with ninhydrin. And if I had to explain why I was doing that, it would be because the amino acids are colourless, so they cannot be seen until sprayed with the ninhydrin, and that's what then allows us to measure the RF values. For part C, we have to deduce the minimum number of amino acids present in the original mixture. So we've got our original spot here, which in solvent 1 separated out into those 3 different components, I suppose. But when we then did the experiment again, in solvent 2, we saw that there was clearly some amino acids that didn't move off the start line in solvent 1, which then did in solvent 2. We can see that this spot is not a mixture at this point, because in solvent 2 it's moved, but there's still only one spot showing. But for these two spots, they've then further split into 2. So that was 2 amino acids on that spot, 2 amino acids in that spot, and there were 2 amino acids in here that didn't move in the first solvent. So we're going to have 1, 2, 3, 4, 5, 6, 7 different amino acids within this mixture. And we can't count them from here and go 1, 2, 3, and then count 4, 5, 6, 7, 8, 9, 10, because this spot is made of that one. So you'd be counting the same one twice. And this is made of them too. So you'd be, counting too many if you do it that way. So we're counting the grey spots because that's once everything, to our best of our knowledge, has been separated. So there's going to be at least 7 different amino acids. And that's why it says the minimum number, I suppose, because we don't know that the second solvent has managed to separate out all of the amino acids. It might be that if we did it in a third solvent and did it this way, that we would then get additional separation. So this spot might then become 2, which is what happened between solvent 1 and 2, but we're not privy to that information. So we can only go off what we've got. And after the second solvent, it shows that there are 7 amino acids. In terms of why it's necessary to use 2 solvents, I would argue there's 2 approaches that we can take here. The first, if we didn't use a second solvent, we wouldn't have known that these 2 amino acids were present because they weren't soluble in the first solvent. And I know that because it is from the position of the original spot in the second solvent that they've then moved and been deposited at different heights up the TLC plate. So one reason why it's necessary to use more than one solvent is because not all of the amino acids were soluble in the first solvent. So we would have got an inaccurate value for how many amino acids there are. The other reason that I would argue you could give is the idea that even though there were clearly some amino acids that did dissolve in solvent 1 and move differing distances up the TLC plate, for them to be separated in the second solvent, showing that there were 2 different amino acids that initially might only have looked like one spot. In the first solvent, there must have been amino acids that had really, really similar RF values in that particular solvent, because that spot is basically made up of 2 amino acids, which only then separated out in the second solvent. Likewise, this spot was made of 2 amino acids, which only separated out in the second solvent. So their RF values in solvent 1 had to be nigh on identical, which is therefore not helpful in deducing how many amino acids there are, but also not helpful in then matching those to the RF values from the database. And I would argue either of those answers is absolutely fine for part D. So option 1 would be to say that some of the amino acids were not soluble in solvent 1, and so they were never going to be able to be identified. Or we can say that some of the amino acids had identical, or at least nearly identical, very, very similar RF values in the first solvent. And either way, if the goal of the chromatography is to work out the amino acid sort of chain for this particular protein, then we're not going to be able to do that if either of those things are true. So second solvent was needed. And this comes down to the fact that any species, whether we're talking about amino acids or other components in mixtures, the amino acids will have different solubilities in certain solvents and different affinities for the TLC plate, and depending on what the solvent is will determine, I guess, the degree of separation. Comes down to the polarity of the amino acids and what we have in the side chain, and that's something that might be asked in other questions. So that's, I guess, the key things for chromatography for this question. There are things like being able to deduce, or rather explain, how the amino acids get separated, so the balance of solubility in the stationary phase, solubility in the mobile phase, sorry, the solvent, versus the affinity for the stationary phase, which is the TLC plate. The idea that that comes down to the polarity, and you always end up with like being attracted to or being soluble in like substances. So if you have a polar solvent, the polar amino acids or the more polar amino acids will prefer to be dissolved in that solvent. If you had a non-polar solvent, the non-polar or the less polar amino acids would prefer to be dissolved in that one. And that's something you might have to explain as well. But the question about anhydrine is very common. The question about using a strong acid like hydrochloric acid as a reagent for hydrolyzing the protein is very common. And also just understanding this idea that there will be different solubilities in different solvents is also quite important. Any questions about that, guys, as always, please let me know. But hopefully that's been helpful. Any requests, as always, for similar questions or different questions, just let me know. And yeah, anything I can do, just ask. If not, I'll see you in another video soon. Thank you so much for watching.